Welcome, everyone, to the second module of Basic Radiological Incident Awareness course. We're going to cover today an introduction to radiation safety. So the Basic Radiation Incident Awareness modules are meant to provide an awareness level training. We did have a 3-day course that we used previously that was in person and included a tour of a nuclear power plant. And so this doesn't really replace it, but it does provide an overview of that course. Recorded versions of all these modules will be at the BS National Training and Exercise Program website, and you see that website here, and I believe it will be posted into the chat. You could also find this on just going to the APHIS VS website and going to Animal Emergency Management and the NTEP website. So the basic radiological incident awareness modules include an introduction to radiological incidents, which Dr. Corcoran presented previously. This one, and then we're going to look at response at both nuclear power plant incidents and in nuclear terrorism incidents. We're going to look at an overview of animal decontamination planning, and then agricultural radioecology and long-term recovery. The livestock mortality management and chemical or radiological incidents is one that I recorded a year or so ago. So the overarching objectives are here, and today we're going to look at the second group of objectives, which is identify the types of radiation measurements, health effects, and protective actions. The reason I'm here and Dr. Corcoran is we're both the members of the advisory team for environment, food, and health, which is a multi-agency One Health federal team from CDC, EPA, FDA, and USDA with other agencies added as needed. We provide scientific expertise on radiation emergencies, and we integrate with the Federal Radiological Monitoring and Assessment Center to provide protective action recommendations. The FIRMAC provides a lot of data collection and data analysis, creates briefing products, and then passes those to the advisory team for us to provide recommendations based on those products and other data. So the module 2 objectives are to briefly describe the types of ionizing radiation, identify the units of measure for radioactivity, radiation dose equivalent, and radiation exposure, which can be challenging with both the international units and the US units currently being used. Briefly describe the effects of radiation on dose and health. Define the term ALARA, which is as low as reasonably achievable, and identify work and protective actions, and identify additional sources for more information on radiation. Starting with a few years back, the CDC and Oak Ridge Associated Universities made a video series called Basic Radiation Basics Made Simple. It's narrated by Dr. Ayman Ansari, who's a member of the advisory team from CDC. And there are these modules here that you see listed, and it is extremely well done. Now, in the 3-day session, we actually had people watch these in person in the class because they're so good. And so that's one of the things I would recommend, in addition to what we're going to hear today, is to go back through and watch that video series. It takes, an hour to 90 minutes. So when we talk about radiation, radiation doesn't always mean ionizing radiation. So if you look at the various types, there's visible light, which we're the most familiar with, which is really radiation or energy. And looking at this spectrum of wave or photon energies, visible light is a very narrow spectrum that we use to navigate our lives, but beyond that, to the lower frequency is infrared, and then we get into the very long wave radiation, microwave, FM, TV, shortwave, AM, and even long wave radiation from power line side emissions. And these are, the long wave radiation is generally not considered to be too harmful, but in very large doses, it can be. In other words, obviously, when you put food in the microwave, it heats up and could be very damaging to a living organism. And people have shown that use of cell phones, by the side of your head for long periods of time over years could be causing some harm. When we go the other way, the first thing we hit is ultraviolet radiation, which is from the sun. And it can cause sunburns and can cause ionization and over long-term exposures can actually predispose towards skin cancer. And then we have, in varying degrees of energy and short wavelength, gamma rays, X-rays. And these types of, all the ultraviolet, gamma ray, and X-ray can actually cause ionizing of molecules within the cell and damage to DNA and other cellular components. So it's just good to understand that when we're talking about radiation here in this presentation, we're really referring to ionizing radiation or those radiations that can cause damage to cells. And when we look at that, not only are there the gamma rays that we just talked about, and they're very high energy, but we also have alpha particles, which are, as a friend of mine described them, the bowling balls of radiation. In other words, they've got two neutrons, two protons, and they get kicked out of a decaying radioactive atom. And we'll talk about their properties in a minute. The other one is the beta particles, which are basically an electron that can be ejected from an atom during radiation decay. Once in a while, you'll hear reference to neutron radiation, but neutrons are kind of like alpha particles. They don't go that far. And so unless you're right around a nuclear reactor or right near a nuclear explosion, the chances of getting neutron radiation are really low. So we don't really normally talk about those too much. Although I've seen some misleading public stuff on social media that really trumped up neutron radiation, which was completely not valid scientifically. When we look at the penetration abilities of radiation, if we look at alpha particles, they're a large particle. They are stopped by a sheet of paper. They usually only travel a few inches at the most in air. And so they're pretty easy to shield against. But the big problem with alpha particles is if you inhale them or ingest them, then 100% of that energy that they carry with them during that decay is imparted to the body. And the next one is the beta particles, the electrons, a layer of clothing, less than an inch of plastic usually is enough to screen from that. If you do get beta emitting radionuclides contaminating your skin, it can cause a beta burn or like a severe sunburn. And so we do worry about those coming in direct contact with the skin. With alpha particles, the dead layers of your skin will actually stop at alpha particles. So externally, they really can't do much of anything. Together, they're considered what some people will term high linear energy transfer radiation. So if you ingest or inhale alpha or beta particles, you will absorb 100% of the energy from that radioactive decay. When we come down to gamma rays, it's very difficult to shield. X-ray aprons will stop most of it, but we can't really go out in the field wearing, head-to-toe lead shielding. So lead shielding, concrete, water, any heavy mass will shield gamma rays. The problem with those is that your regular Tyvek PPE doesn't do anything to shield against gamma radiation. The good thing is that gamma radiation, if internalized, not all of it will be absorbed when it decays. In other words, when you take an X-ray of your hand, you don't
you see a picture of your hand with the bones and soft tissue. And so some of the X-rays are absorbed by your tissues, but a lot of it comes through and then hits the X-ray receiving plate. And so it's called low LET radiation because it doesn't all absorb into the body. Okay. So another important concept is half-life. And so whenever a radioactive atom decays, releases a radioactive particle or wave, it turns into another type of radionuclide. And so it could go to a stable element that is no longer radioactive, or very commonly you'll see a radioactive element decay, become another radioactive element, which then decays, et cetera. And we'll look at one of those a little bit later. But so if a half-life brings it down 50%, by the time you get down to 7 half-lives, there's less than 1% of that radioactive material remaining in that original form. Like I said, sometimes you'll still have some radioactivity if they don't decay to a stable substance. And so it makes a huge difference when you're talking about something that has a half-life of a few days versus something that has a half-life of 20,000 years. When we measure radioactivity, there's some challenges because there's, much as inches and miles versus meters, centimeters. We have two different systems of measurement being used in the world. The old measurement is the Curie. And if you think of radiation as a disintegration per second, as the unit of radiation, then a Curie is the amount of radiation produced by 1 gram of pure radium. And when you look at the becquerel, it's really just 1 disintegration or 1 decay per second. And so that the Curie is about 37 billion becquerels. And so I hope you can see that there could be some real challenges with communicating radiation units. And so if one person is talking picocuries, which is 1/1000th of a Curie, another person is thinking becquerels, you're off by 3.7. If you're talking Curies versus becquerels, you're off by a factor of 37 billion. But, you talk about kilobecquerels and picocuries, and the radiation units get very confusing very quickly if you're not careful. When we talk about dose equivalents, which are the most common thing we use in response, there's a rem and then a sievert, and 100 rems equals 1 sievert. But of course, you talk about millirems and microsieverts and millisieverts, and it really does leave the door open to misunderstanding, and the media could easily, and the general public could easily get confused and substitute the wrong unit in the measurement. When we talk about less commonly used in response is exposure, what is emitted, and that's a Rankine and Coulomb per kilogram, and the amount of absorbed dose, which is a rad or a gray. And rads and grays for gamma radiation are really similar to REMS and sieverts for the average responder. So when we look at how much radiation we get on a normal year, about 50%, well, it's up to about 6.2 millisieverts or 620 milligrams per year is the estimate. This is from 2009, I think. And it hasn't changed much, but about half that comes from background, the cosmic radiation from the sky, the radiation from the earth, the radiation coming from in your own body, the air you breathe, the food you eat, et cetera, et cetera. Medical also accounts for a little less than half, and consumer and occupational exposures really account for very little. Actually, nuclear power plant workers are so heavily monitored, they really have pretty low exposures. Airline crews actually have one of the higher exposures of all the professions, and we'll get to that in just a minute. So average medical exposure in 1980, when I graduated from vet school, was about, 50 millirems per year. And 10 millirems is about a chest x-ray. In 2006, that was up to 300. But we're talking about CT scans and nuclear medicine and just a lot more use of radiological diagnostics, which is actually good because some of the, if you ever compare a regular x-ray to a CT scan, there's just no comparison whatsoever as far as the diagnostic value. So we're going to go to the first polling question. And so the radiation dose that you see the portal screeners at the airport that you walk through, the wave portals, and what would be the equivalent of that one walk through at the airport to a round trip? Well, how many of those would you have to go through to get the same radiations you'd have to get compared to a chest x-ray or a round trip between London and New York? So let's see what everybody thinks. And I won't do it because I already know the answer.
I'll give everybody about 10 more seconds before we end the poll.
And I think the answer will kind of reassure you that if you're going through a portal monitor at the airport and then getting on an airplane, the portal monitor is the least of your exposures.
Okay, I'm going to go ahead and end the poll.
And the answer,
share the results.
Well, everybody's all over the place. And the answer is it's 1,000. You'd have to go through that airport screener 1,000 times to get the same dose that you're going to get on a round trip to from London to New York. So hopefully that makes everybody feel better about going through airport screening. So if we look at airport screening, 0.01 millirem or 0.1 microsievert. And New York to London by air 5, chest x-ray 10. Annual food exposure is 30 millirems. Natural background was about 300. All this varies. If you're up in the mountains in Colorado, you're going to get about 10% higher at least. A CT scan of your abdomen is 1,000. And if you're really sick, you don't blink an eye at getting that CT scan because it can save your life. But it's a fairly significant exposure compared to some of these others. And the occupational limit is 5,000 millirems or 50 millisieverts. You will see some blood changes at about 25 rems or 25,000 millisieverts and or 25,000 millirems. And that at 1,000, or excuse me, at essentially 1 sievert or 100 rems or 100,000 millirems, you will see the onset of signs, primarily gastrointestinal signs of radiation sickness. At 4,000 millirems or 4 sieverts, you will get about a 50% mortality rate if people are untreated. Now, with treatment, in some of the bad radiological incidents they've seen, the survival rate is actually much higher than that at that exposure because they're going to treat people. But once you get up to about 10 sieverts, that's fatal in almost all cases, although some people have survived doses like that. And if you're doing radiotherapy, where you're just focusing on a small area of the body, you can put in a tremendous amount of radiation to kill the tumor. And typically they rotate how that's delivered and then focus on one spot where the other tissues don't get near as much. Okay, so, but I hope this gives you some perspective. And Dr. Ansari in in the video series uses a pinto beans to kind of give you a visual of the differences between something like this and then something like this. It's just obviously a huge difference. And I don't think he even uses this one. I think he uses something more in this range, because if you had to get for 40 million pinto beans in jars, it would take a while. Okay, so next concept is radiation versus contamination. And radiation is really just being exposed to ionizing radiation energy. And the exposure ceases when you're removed from the source. So if you're out there laying in the sunshine getting UV radiation, you walk indoors, it's gone. If APHIS has irradiators in certain countries that irradiate fruits and vegetables coming into the US to make sure they're not carrying certain pests, but they go through either a gamma or X-ray machine, they get an exposure, but when they come out, they're not radioactive and they're normal again. Contamination is when you get radioactive material that's deposited on the outside, either on your skin or your clothes, or internally if you inhale or ingest it. And until it's removed from on top of your body or from within your body, you continue to receive exposure. So very important to think in terms of radiation versus contamination. External contamination, skin and hair, relatively easy to measure, and decontamination removes most, although some radionuclides really like to stick to hair. And then internal, either GI tract, respiratory tract, it could, if you were in a nuclear detonation and you might have wounds and contamination inside the wounds. It's much more difficult to measure the alpha and beta radiation internally because it's blocked by the body. And so sometimes you have to go to pharmaceutical lab tests, testing urine or feces or blood to be able to detect that contamination. And for almost every contaminant, there is a medication to help remove that from internal contamination. Most of them have other uses in toxicology. And so, there are ways to treat internal contamination that are at least reasonably effective. Okay, so most of you probably are thinking, man, I haven't seen a periodic table of the elements for a long time. But when dealing with radiological incidents, this is actually an important tool to get an idea of what radionuclides are present and how they behave chemically as far as for health impacts. And there's a really good website on radioactive isotopes in medicine, and it's almost all applicable equally to animals. And so this radiological emergency medical management site from the National Library of Medicine is a great program. You can get it for your phone. You can access it from your computer. It's just really a great reference. So we're going to look at some of these radionuclides and we'll see how they affect the body. So the most common radioactive substance in living organisms is potassium-40. And it has a very long half-life of 1.25 billion years. And it's a primordial radionuclide. In other words, it was formed, it was there when the Earth was formed. And so it's just gradually decaying. There's half as much as there was 1.25 billion years ago. It decays by both gamma radiation and beta, and has a very short biological half-life. In other words, if you take a potassium supplement, that potassium enters your body, but you excrete quite a bit of it. And so there's kind of an equilibrium. So every time you take in potassium, you get rid of some, and it's very mobile. And if you get and potassium-40 stays stable because it's present in all forms of potassium on Earth. And there's about 5,000 becquerels, in other words, 5,000 disintegrations of potassium-40 per second within your body. And it accounts for about 1/10 of the natural annual exposure. And I hope that allows you to see that, we live in a pretty radioactive world. And you don't want to stop taking in potassium because you're worried about the radiation from potassium-40. Whenever out of every 10,000 potassium atoms is potassium-40. But if you stop taking in potassium, you'd eventually die. And if you look at some foods that are high in potassium, bananas and plantains, and this is Brazil nuts here, which is probably the highest potassium food there is. Okay, so if we look at the various other things, cesium-137 and cesium-134 are two nuclear fission byproducts. In other words, they're made in nuclear reactors. If there's a nuclear detonation, there's quite a bit of this made from the fission of the primary fuel. And cesium-137 has a half-life of 2 years, so it's gone pretty quickly, but a half-life of 30 years for cesium-137, so it stays around a good long time. And it's a nutritional analog of potassium, and if you look back on that periodic table, you look at potassium and sodium up in that column, and then you'd follow it all the way down a ways, and you'd find cesium. It also has a short half-life biologically, and has an affinity for living organisms, soils, and actually migrate into concrete too. And very high energy gamma and a bit of a beta. And it's extremely useful for cancer radiotherapy because of the high energy gamma emissions. So next we'll look at iodine-131, also a product of nuclear fission. Normally likes to be in a gaseous state, although it can be incorporated into living animals and plants, and has a half-life of approximately 8 days. So that's really nice because in approximately 2 months, there's only 1% left of any radioactive iodine that was produced for the incident. It does both beta and gamma radiation, which makes it easy to find with a detector. And it'll concentrate in the thyroid gland and will cause damage to the thyroid gland at levels that are maybe lower than what you'd be concerned about for whole body exposure. And so high doses cause an increased cancer risk, and potassium iodide tablets can prevent iodine-131 uptake. It's a competitive inhibitor. In other words, if you take stable iodine prior to the exposure to iodine-131, you've got so much stable iodine in your system that you don't take up much of the 131. If you don't start taking potassium iodide for 2 or 3 days, then the iodine's already been taken up in your system and done the damage, so it doesn't really help very much. And potassium iodide is promoted as a radiation protection pharmaceutical. It only protects against iodine-131. It doesn't have any effects on any other type of radionuclide. So strontium-90, also a fission byproduct. It's purely a beta emitter, which makes it harder to find. And then it has a 28-year half-life, so very similar to cesium. It's a nutritional analog to calcium, which means it can you'll see it in soils and bones, and it has a much longer biological half-life. So strontium can be a big concern. It's obviously a concern for agriculture as well. So we're going to do another poll here, and the question is, the plutonium-238 that powers the thermoelectric generator in the Mars Perseverance rover has a half-life of, and your choices will be, when that comes up, of 2.5 years.
I brought the wrong one up. Here we go.
Okay. So 2.5, 10.9, 24.3, 87.7.
Yeah, I'm sorry, Dennis. I don't have this one.
Oh, okay. Well, we'll just hang out for just a second and let people guess.
Okay.
But,
you can put it in the chat.
Yeah, Yeah, I'm not sure if I can see the chat.
I can let you know. So we have
Okay.
24.3, 10.9, 87.7, 24.3.
So just as a comparison, the Opportunity rover, which lasted almost 15 years on Mars, when it had an expected lifespan of 90 days was their goal, managed to stay active due to its solar panel charger. But the solar panels became dust covered and had a lot of wear, and eventually it lost power and quit working, even though it was way beyond its expected time. But the half-life in the 238 power generator has an 87.7-year half-life. That means the Perseverance and the Curiosity rover literally could run for decades and decades off that power source, and most likely something else will fail before the end of the rover's lifespan. Okay, so then we'll talk about the actinides, uranium-235 and 238. 235 uranium is the one that can be used for fission, and plutonium-238, 239, there's several others too. 239 is used for nuclear weapons, 238 for power generation, and you have americium, thorium, radium, there's a number of others. There is a new type of fuel that I think uses a slurry of thorium and uranium-233, I think, that's being looked at for the small modular reactors. But these are all very useful in nuclear technology, and they're mostly decayed by alpha radiation, and they're also, a lot of them are chemically toxic. So uranium, even if it's not even the depleted uranium, if you eat enough of it, it can cause some problems. The last one is tritium, which is a stable hydrogen, has one proton. Deuterium has one proton, one neutron, and tritium has one proton and two neutrons. So people call it heavy water. It decays by beta emission, and then has a half-life of 12 years. It's created by ionizing radiation interacting with water in the upper atmosphere. In other words, catching a neutron from space and having those neutrons absorb into water in the air. And it's used, it's got a lot of industrial uses, such as in watch dials, tritium, gun sights, things like that, and highly mobile in nature. And if we ever get fission worked out, one of the, for nuclear fusion, in nuclear weapons, they use heavy water infusion into the nuclear blast. And then in some of the fusion models, they use tritium and deuterium for fuel as well. And they were just in the process of releasing a bunch of tritium from storage at the Fukushima nuclear power plant. And people are worried about it, but diluting it in the ocean really makes it a pretty safe mechanism to get rid of that tritium. So we're not going to go through this in depth, but radium is one of the actinides, and it was the element that Madame Curie and her research crew really worked with initially, and then radium became a really interesting element for its uses in various forms. And there's a great story about radium on YouTube that's probably worth watching, and about the focus on the watch dial painters, the women who were initially hired to paint watch dials with radium-laced phosphorescent paint, and how it wasn't till a few years later they realized that they were seeing just incredible rates of cancer in these unfortunate women. There was a lot of radium quack products released back in the early 20th century, including a product called Radithor. And there was a really high-profile case of a guy named Eben McBurney Byers, who was a wealthy amateur golfer. And he started promoting Radithor and from a prescription from his doctor. And in that point in time, doctors actually got kickbacks on all their prescriptions. And so from 1927 to 1930, he consumed about 1,400 vials of Radithor. And then in 1932, he developed a brain abscess and osteoporosis, and also had cancer, and died as a result of that. And what they did is, this was kind of when the light bulb went on and realized that radioactive elements were not completely safe. And so FDA increased its authority dramatically related to this, as far as trying to get rid of quack products, and we're able to start regulating radiologically active pharmaceuticals. And there's at Oak Ridge National Laboratory, there's a museum of radiological things, including all these quack products. So we're going to talk a little bit about radium as an example of how radiation and decay works. And radium and its daughter elements are a significant part of natural exposure for everybody. There's 33 isotopes of radium. They're all radioactive. And it's part of the natural decay chain of uranium and thorium. And radium decay produces radon gas. And there's an established EPA limit on radon in homes, which is 4 picocuries per liter. And if you want to, you can change that to, becquerels if you'd like. Yeah. And if you look at this, since there's a lot of different radium and radon isotopes, this decay chain isn't exactly true in all cases, but it's a good example. And you can see it's going from alpha decay and beta decay down, and it goes from days to minutes to milliseconds here to 22 years for lead-210 and polonium-210, 138 days. And so really, what's really important about radon gas isn't that the radon is causing that many alpha particles, but for every radon that decays by an alpha particle, there's also a whole bunch of alpha and beta decay in this series that produce additional radiation exposure. And it winds up being, it all ends up at 206 lead, which is a stable isotope. So we're going to have a little quiz here, and there should be a poll for this. So if you've got high radon levels in your home, A, does that require dramatic remodeling of the home? B, those high levels are much more dangerous to smokers than non-smokers, are a leading cause of lung cancer in people, and are the most common in clay soils. So we'll give everybody a chance to answer that. We'll start out by talking about the research on the effects of radon in homes when they started regulating it. There was a good study that showed that they looked at lung cancer rates versus primarily two factors. One is the amount of radon in the home, and number two was whether people smoked or not.
Okay, I'm going to go ahead and end the poll.
Okay.
And here's the result.
Okay, so the study really showed that radon presence in high radon in homes for people who didn't smoke had a very, very tiny impact on lung cancer rates. But people who smoked, it had a dramatically higher rate of lung cancer. And that's because of the additive effect of the radiation from radon, along with the chemical and radiological exposure to the lungs with tobacco. Tobacco is notorious for accumulation of polonium and lead-210 isotopes. So, and that's what radon produces. So it doesn't really require dramatic remodeling the home. Our house, when we lived up in the mountains southwest of Denver, an hour or so, it was like $1,000 to make it the whole house. It is much more dangerous to smokers than non-smokers, and so that's the correct answer. It's not the leading cause of lung cancer in people, that's smoking. And it's actually most common on soils that have a lot of granite content. So, if you go up in the mountains of Colorado, sometimes you'll have a lot of radon in homes, but it's an issue nationwide. So, okay, here we go. So we're going to talk a little about nuclear fission. Nuclear fission is just really splitting an atom. You take a uranium-235 or 239 atom, and you hit it with a neutron, and it will split. And it doesn't always split exactly the same way. And that's why there isn't just two major fission products. There's literally dozens and dozens of fission products that you can get after a nuclear detonation, for example. But it also releases some additional free neutrons, which can create more splitting. And so in a chain reaction like this, if you control that chain reaction, you can get a nuclear reactor and just get heat and run a power turbine. In an uncontrolled reaction, if you push two pieces of plutonium together, you can get a criticality. They'll blow themselves apart and release a lot of radiation, and wouldn't be a full nuclear explosion. If you compress that, either by compressing it through an explosive or a high energy impact of one piece of uranium into another, you can get a nuclear detonation. And then if you infuse heavy hydrogen into it, then you can get a hydrogen bomb. And so that's the basics of nuclear fission. The Trinity test was the first in New Mexico. It's just towards the end of World War II, and then it was used in Hiroshima and Nagasaki. And then obviously there was a huge amount of above ground nuclear testing post World War II that was curtailed in the 60s. So we know about high dose radiation and cancer rate. We know that if you get exposed to a large amount of cancer, they looked at people in various nuclear incidents, and they could see a linear relationship to exposure and cancer. And so there's what's been used for setting standards for radiation safety is what's called the linear no threshold model, and I'll get to that on the next slide. But really, the question is really what is happening at those low level doses, and there's a lot of people interested in this, both medical and health physicists, industry and the nuclear power industry, the military, aerospace sector, emergency management, agriculture, and the public really want to know what it really means when you get a radiation exposure. And so the linear no threshold concept is it just keeps going down until it hits zero at zero additional exposure. But that's really not been epidemiologically validated. Part of the challenge is that there's about a 40% lifetime cancer risk for people. And that includes all types of cancers, including things like skin cancers. And so it's not a 40% fatal cancer, but that's a pretty high incidence. And so trying to tease out really low levels of exposures within the epidemiology of a high prevalence of cancer in people from all sorts of things, ranging from radiation to chemical to viruses to genetic predispositions. So it's been really difficult. And so there was, starting in the 90s, there was a Department of Energy funded low dose radiation project, which wanted to understand the effects of those low doses below 10 rems. And they're also doing epidemiological studies at Oak Ridge Associated Universities has the 1 million person study ongoing right now, where they're trying to tease out data and try to compare people in various risk groups with known exposures, with similar medical backgrounds, and try to decide in these low doses, are we getting higher rates of cancers of various types based to the expected amounts in the general population. And the European Union has their multidisciplinary European low dose initiative, which is doing both academic research as well as epidemiological research. And so this is kind of an exciting time for trying to figure this out, because when they've done the low dose studies at Department of Energy, they found things happening at the cellular level that were unexpected. They saw that cells seem to be able to communicate radiation injury to cells in the immediate area around them, even though they weren't exposed. They saw cells that would undergo almost pre-programmed self-destruction at a certain radiation dose. They found that cells exposed to a 1 rem exposure, this is cells in a cell culture, and then turn around 2 or 3 days later, exposed again, were actually much more resistant to the radiation effects. So a lot of things are happening right now as far as low dose radiation, but the end version is that our current standards for radiation safety appear to be not only appropriate, but highly conservative. So I'm not suggesting that we need to change our standards at any point in the near future, but I think it validates that we are using response and industrial worker standards that are really safe. The EPA has a Protective Action Guide manual, or the PAG manual, that has federal guidance for preventing avoidable future dose. And there's multiple things in here, and we use the PAG manual a lot in the advisory team. But exposure limits, evacuation points, water limits, food, and so we'll cover that a lot more in the modules on response. So now we're going to go to basic radiation safety. We're going to talk about HALARA and ways to avoid dose, monitoring and dosimeters, and then personal protective equipment. So HALARA means as low as reasonably achievable. And that's really a baseline standard within radiological response. And while we have our PAG recommendations and our worker protection information from OSHA, in less complex incidents where there's not a lot of exposure, we're going to try to keep those thresholds not only below those recommended limits, but as low as we can. And so, if someone has a potential spill of a medical shipment containing radiological materials, they're going to be real careful, even though maybe the dose in there isn't enough to really do much of anything. They're going to just be real careful and try to not expose anybody any more than they have to. In a catastrophic incident, such as nuclear detonation, we may actually take that PAG manual and go to higher limits, because there are other hazards out there that are more life-threatening than the radiation exposure. In other words, people need to get somewhere safe. They need to get their injuries treated. They need food, water, shelter. And some of those things are actually more dangerous than the radiation exposure they might be getting. So just remember that, we want to use this HALARA type principle, but we also want to be paying attention to the whole incident and not put people at additional risk over concerns over very low levels of exposure. Time, distance, and shielding are the three primary ways of reducing exposure. Time is pretty obvious. If you get if you're getting 10 millirems per hour exposure, if you cut the time there in half, you'll get half the exposure. And if you get farther away, that's inversely proportional to the distance. So if you're standing twice as far away from a radiation source, you're going to get a quarter of the exposure, 4 times the distance, 1/16 the dose. If you're several miles away, obviously you're going to have, very, very little, if any, exposure from it. And shielding is easy for alpha and beta and difficult for gamma. And we kind of talked about this. Alpha particles, really just both with alpha and beta, for the most part, we just don't want those getting inside the body. So use of personal protective equipment and making sure that you don't inhale or ingest those materials. Beta, we are a little bit concerned about a lot of beta releasing material being on the outside of your skin, causing the burn. Gamma rays, really, you need that thicker concrete or lead shielding, and walking around doing stuff with that on is not realistic. So, but if you're taking x-rays or working in a medical field around radiology, then yeah, you're going to be able to use the shielding. You're going to have a control booth behind a shielded wall and shielding on that you can wear if you have to be there. Zones, when it comes to exposure, zones are used a lot, and zones can be incredibly confusing in radiological response. If you look at some of the standard definitions, IAEA and the US will apply some of these in some circumstances, but in a lot of the FERMAC maps, you'll see something like a dangerous fallout zone, a very high radiation zone of greater than 10 rems per hour. And that's really a zone where nobody goes unless there is an absolute critical life-saving need there that can be done in a very short period of time, because at 10 rems per hour, in 2.5 hours, you're going to hit some blood changes. At 10 hours, you're going to start getting radiation sickness. At 40 hours, you're going to get 50% potentially fatal exposures. And it could be a lot higher than 10 rems per hour. So obviously there's times where you just don't go there. The hot zone is poorly defined, but IAEA and some other sources usually call that the 10 MR per 10 millirem per hour, 0.1 millisievert per hour. And a controlled access zone is going to be is going to be the evacuated zone between there and the hot zone. So it may start at 2 times background, but it may vary quite a bit with the incident. So just be careful that in a radiological incident, for the incident itself, you're probably not going to see hot zone, warm zone, cold zone terminology used much. It's really going to be identifying either actions. In other words, it could be the evacuation zone, it could be the dangerous fallout zone, et cetera. There's evacuation zone, which are based on dose over the first 4 days, and relocation zone, which are based on the amount of exposure that you would get over 1 or 2 years staying there. And so the evacuation will be first, then you'll get a relocation process later, and then the people can actually hopefully go back to their homes after a while with the relocation zones. And then the agricultural control zone is a zone in which most of it is not even evacuated. It's based on long-term food chain bioconcentration, and it's not in the hot zone except for a small amount of it. It's mostly going to be in the non-evacuated zone. And there's some more stuff about zones in the REM site. So I hope I haven't confused that too much. Now, when we come to decontamination operations, yeah, we'll use the typical hot zone, warm zone, cold zone. But just be advised that the entire decontamination process, such as at a community reception center, the actual process may be happening in the cold zone. But you have people coming in and they're stopping it here, and then that becomes the hot zone for decontamination purposes. So just be careful when you're thinking about zones and not get too wrapped up in terminology till you know exactly what it means. Monitoring dosimeters, you have the little pencil dosimeters up here in the top, which you can look through and see how much exposure you've had in primarily gamma radiation. And then you can, at the end of the day, turn that in, they'll read it and then reset it and give it back to you. And they're fairly cheap. You can get these digital ones that do the same thing, but they can also track exposure over a much longer period of time. And then you can get these personal radiation detectors. Some law enforcement people will carry those routinely just in case they run into a radiation situation that was unexpected. And they vary hugely in costs. Survey meters measure radiation, and they either have a probe like the one on the upper left, where you can go over a person or an animal and check all up and down their body and look for any areas that are contaminated versus others. Or these other ones are used to measure area radiation. So if you had a crew that was working out in the field, you might have someone with one of these lower ones there just to look at the ambient radiation of wherever you're working. So one more question here. And the question is, the typical PPE, personal protective equipment, for agricultural responders in a radiological incident is nearly the same as in an animal disease incident. True or false? So what do you think? That's an easy one. I mean, you got two choices, so happy you're going to be right no matter what, right? Are we ready to close that out?
Just about. Just waiting to see when we stop. Okay, we're going to go ahead. Give them about 5 more seconds, and then I'm going to go ahead and end it. Okay, there's the result.
Oh, boy, sounds like a 50-50 guess. The answer is it's almost the same. The only real difference is that there's nuclear power plants tend to use N100 masks instead of N95, so they're a little bit thicker. But really, it's the same thing. You're just trying to avoid inhaling or ingesting. And so PPE, Tyvek, gloves, boots, hood, a respirator, it's just really the same. So when it comes to the PPE, it's really almost the same. And in fact, if you're in the agricultural response, if you're out in the unevacuated areas in the agricultural control zone, the only PPE you need is what you would normally wear to a normal farm visit. So if you're way out in the control zone collecting milk or soil samples, I mean, just whatever you would wear to a farm visit. If you show up with a white Marshmallow Man suit and, you're going to be freaking everybody out and not really doing anything but causing yourself a lot of discomfort. Okay, so we talked about this, protect the skin and their organs from internal contamination. And really, your gamma radiation exposure is just based on time and distance and using personal dosimetry for anybody that's in a controlled access zone. So here's what we just talked about. And really, if there's a radiological incident, there will be safety officers, there will be radiation safety officers, there will be OSHA personnel, there'll be state personnel. The decision of what PPE needs to be worn in what areas is really going to be powered by these radiation safety experts. So, they'll let you know what you need. This is a little bit of here's the RAD Basics video series we talked about. There's CDC has radiation emergency training and safety education, which you can get CE credits for, RACE credits for, but I'm not sure if it's for veterinarians. But there's some good training there. California has a basic radiation science course on YouTube, and radiological emergency medical management has some really good material in it. The other thing that is, as we go on, there are some actual in-person courses you can take that will provide those at a later date. So here's my speaker contact, and I guess at this point, I'm happy to answer any questions.
We do have a couple questions in the chat, although Robin, thank you. You were answering some of them as we were going. One of the questions that I thought was interesting, what occupation within BS would have the potential to ionize and radiation exposure outside of an emergency response to a radiological incident?
Well, I'm not sure about VS specifically, but anybody using radiological diagnostics. In other words, Animal Care does the horse protection program. They X-ray feed, and so they are in a radiation protection program directed by the Radiation Protection Branch of the USDA. And so any X-ray material, that's probably the main exposure. I suppose in an emergency incident of some sort, you could wind up, if there was a radiological component of it. That's really the two main things.
The other question is, nitrile gloves are protective also?
Yep, if they keep dust from coming in, they'll do a good job. They won't protect you from gamma radiation. And if you got a lot of beta radiation on your gloves, you might get a burn. But for the most part, yeah.
And then another question is, what about washing usual PPE such as coveralls?
Yes, I mean, quite honestly, the biggest thing is you don't want to inhale or ingest. If you're working in a contaminated environment, and when you doff your PPE, you've got some external contamination somehow, then you should just go through a decontamination process and bathe that off. So it's if let's say we had a radiological incident and you're on the agricultural response and you're in an area where there's controlled access, you need to wear PPE, but it's 95 degrees and 95% humidity, would cotton coveralls be an option? And the answer is they might be. They might be less hazardous than Tyvek in that type of environmental condition.
I just want to let everyone know that these webinars have been recorded. They will be eventually on the NTET video gallery. I have put the link in the chat. I could do that again for everyone. And if you have any other questions or concerns, you can also get in contact with Dr. Dennison or Dr. Corcoran. And we will see you hopefully on our next webinar, which is on Thursday. As soon as we hang up here, I'm going to go ahead and send you the connection information on that webinar. Any other questions?
There was one comment about sweating through PPE can cause
Yeah.
problem. Yeah, and I mean, personal protective equipment has never been considered to be, unless you're in level A, there's always a chance for problems. And the nice thing about radiological incidents, compared to working around Ebola, for instance, is when you get your PPE off, there should be somebody standing there with a monitor and then go over you and see if you've got any residual contamination. So you can measure it in real time and remove it. So whereas if you're dealing with pathogens, whether it's avian influenza or all the way up through, some very bad ones, I mean, if you have a lapse in your PPE, do you really even know what happened? Which can be even more dangerous. I tell people doing decontamination that radiological decontamination is actually safer because you can measure it in real time, it's there, and you know how much radiation you got from it, and in the worst case scenario would be maybe a very slight long-term cancer risk increase for a very high exposure. If you're doing floodwaters, there's things in floodwaters that could kill you this week. So, big difference.
The other question I saw is this credit bearing. I'm not sure what that means.
The what theory?
Is this credit bearing? I'm not sure if anybody.
I think they're asking, does this have CE credit?
No, it does not. No, there's no CEs
Yeah.
attached
No,
to these. I'm sorry.
The race approval process is actually pretty arduous.
Oh, it's horrible. Let me
Yeah.
tell you. I could go on about that, but it's very, very difficult. And it's really too hard to try and make sure that we can do that. So, unfortunately.
But it's free. So there you go.
There you go. The webinar is free. Yeah. All right. Well, I hope everyone has a great afternoon. Watch your email. I'm going to send out the connection information for Thursday's webinar and hope to see you there. Thanks, everyone.